Yes, can you hear me okay?
Yes, I can hear you. Can start.
Okay.
So I have
Yeah, so
roughly 15 minutes. Thanks.
thanks very much for having me in this meeting. So I will talk about a little bit of a change of subject, so moving into neutrino physics. So but just the pictures I'm showing here are at CERN, are the largest liquid argon detectors in the world, and they are currently at CERN. So can you move to this next slide? So I will, since the most of the subject was high energy collider physics, I will talk a little bit about the goals, the open questions in neutrino physics, describe Dune, and then a few words on how we are organized, how we came to be in Dune, how we are organized, what our contributions are and have been, especially at CERN, at Proto-Dune, and then future prospects in collaboration with Brazil. So next slide, and next, please. Okay, so this is just a very quick overview of the current status of neutrino physics. So we now know that neutrinos are massive, and so therefore that they mix, and analogously to the quarks, that mixing is ruled by a 3 by 3 matrix called the PMNS matrix. And so the mass states really are linear combinations of flavor. This matrix is typically parameterized as we have here. So we have a combination of three different mixing angles and the two mass splittings. So there is currently a very strong consensus because there's a lot of evidence for this three flavor picture from many different sources: solar, reactor, atmospheric, and beam neutrinos. So what are the open questions? Next slide. So we know that neutrinos have very small masses, many orders of magnitude below the charged fermions. However, it's very unclear why their mass is so small, and because of that, if that points to Higgs or seesaw mechanism or different mechanisms for the mass generation. We also know that neutrinos are coupled to the charged leptons via charge-weak interactions, and there's flavor mixing. However, it's still unclear if the oscillations are exactly the same for neutrinos and antineutrinos. We also know that they're the only neutral elementary fermion, but we don't know if it could be its own antiparticle. In principle, it could because it's neutral, but that is still unknown. Also, in terms of impact in not only the early universe, but even currently the large scale structure of the universe, neutrinos are super abundant in the universe, very similar to photons. So their mass is important for this structure, and we still have we still need to know what role did they play in Big Bang and the matter-antimatter symmetry. Next slide, please. So going now to more actual questions that we can answer with experiments, so less general questions. So what is the ordering of the neutrino masses? We know that they have masses. We know that there are three masses. We know that mass 2 is larger than mass 1. We don't know if mass 3 is heavier or lighter than the other two. So that's the mass ordering that we still don't know. Dune is probably the best experiment in the world to answer this. Then are neutrinos Majorana or Dirac? And so what is the effective Majorana mass? So that is a question not for Dune, for double beta decay experiments. We are also involved on that. But coming back to oscillations, this three by three matrix picture, is this the correct one, or is that matrix possibly non-unitary and so part of a larger picture? That is still unclear. I mean, it could be unitary, it could be not. And also the question of a very important question is if there is CP violation in leptons and if that is enough to explain the dominance of matter over antimatter in the universe. We know that because the CK matrix is very diagonal, the Yarlskog invariant is very small for quarks, and for leptons it could be much, much higher. And this quantity actually drives the impact that CP violation can have on matter-antimatter asymmetry. So this is clearly something that could be answered by future long baseline neutrino oscillation experiments, such as Dune. Next slide. Okay, next one. So the Dune overview. So Dune is a massive project that comprises a very big upgrade to the accelerator complex at Fermilab. So it will eventually be the most powerful new proton injector in the world, producing the most powerful neutrino beam. This neutrino beam will be fully characterized by a near detector that would also be constructed at Fermilab. And then a neutrino beam will travel 1,300 kilometers towards South Dakota, the existing Sanford lab, where new caverns have been excavated and will install eventually 4 detectors, but in the first phase, 2 detectors with on the order of 20 kilotons each total mass of liquid argon. So next slide. So the Dune approach is unique in the following sense. So the plot that is on the middle left shows the energy range of the beam. So it's a wideband beam, and as you can see, it covers the oscillations over more than one full period of oscillations. So this is pretty unique for beam experiments. Typically, they have narrower energy bands aimed at just one oscillation maximum. Here we will cover 2 of them. So that gives us much more bigger sensitivity to several to extensive phenomenology. Also, it is the longest baseline ever, so that means that we will be sensitive to effects of the propagation of neutrinos through mass. Okay. So since there is some degeneracy between mass matter effects and CP violation, that means that we will be able to measure those asymmetries between neutrinos and antineutrinos, the ones that are related to mass and the ones that are related to CP violation, all in the same experiment. Okay, in the interest of time, I think I will move on to the next one. So the technology is the liquid argon time projection chamber. So in fact, this technology was invented at CERN by Carlo Rubbia. So it was developed over many years in experiments such as Icarus and Microboon, which are now at Fermilab. So the big advantages of this kind of detector is that it can be massive. Liquid argon is reasonably dense for a liquid, so it's good for to be a neutrino target. And also it can have precision tracking over these huge volumes. Precision tracking is basically defined by the wire, by the pitch of the readout wires, which will be around 5 millimeters for Dune. And also it detects all charges. So it can do full calorimetry of the full event. So this is an advantage, for instance, with respect to water Cherenkov experiments such as Super Kamiokande and Hyper Kamiokande. So we'll have 2 different technologies for fire detector 1. We will have horizontal drift. So these planes here on the bottom left, you see alternating planes of anodes and cathodes establishing a horizontal field that drifts the charges produced in the event towards the readout planes. And the new technology has been recently developed by the Dune collaboration to optimize the number of readout channels, optimize the available volume, which is the vertical drift technology, which is also being tested at CERN now. So here's an example of an actual data event from positron at Protodune, so you can see that the quality and the amount of detail of these detectors is outstanding. Next slide, please. Okay, so what are we doing in Dune? So this is the Dune group. So we have several senior researchers and currently three students. All of us are LIP members, and there's a fair amount of overlap also with other experiments. So we do bring much expertise from other areas such as AMS, Atlas. LZ and XLZD. So some colleagues already have cryogenic experience, but also SNO Plus and SND for more neutrino physics experience. Next slide. So as Nuno already mentioned before, LIP is organized in three different poles. So it's a single institution, but with three different poles. So similarly to the Atlas group, the Dune group has people in all three poles, but we function as a single group. But LIP is the single Portuguese institute that participates in Dune, that provides coordination, the institutional representation in the boards, researchers, technicians, labs, computing, etc. But we do function as a single group. Moreover, we do have a close connection to the local universities where some of us are professors and the students are enrolled. So next slide. So some history of how we joined Dune, how and why. So we first joined the neutrino physics in 2005 by joining the Sudbury Neutrino Observatory. We were involved in the optical calibration of the detector and neutrino oscillation analysis. So this was famously the experiment that led to the 2015 Nobel Prize for the discovery of neutrino oscillations. And so we had, I mean, I was a member of Queen's University before. So you can see also here that Art MacDonald visited LIP when we were already hard at work on the follow-up experiment, which is the SNO Plus experiment. So we were a founding member of SNO Plus, and we contributed to construction of two different calibration systems, which are both currently working. And right now we are one of the largest groups in SNO Plus with many responsibilities in data analysis. Still, we wanted to have to balance involvement in a running experiment also with a more future experiment, and also the CERN connection was a very strong motivation to join Dune. The fact that the Dune collaboration and the Dune experiment was being formed, joining people from the US and other parts of the world and Europe with a strong CERN contribution, that surely was a strong motivation to join, because for us the participation at CERN is essential for the stability of particle physics in Portugal. So then, but as you can see, we had already some history of participating in neutrino physics and building these calibration systems. Also, our track record in SNO Plus has in fact opened several doors when we entered the dunes. We didn't enter at the beginning, we entered in 2018, but immediately we were invited to lead the new calibration consortium, and now we do have the leadership of the Dune Calibration and Cryogenic Instrumentation Consortium, one of 11 consortia that's tasked with building the experiment. So next slide. So now about exactly our contribution. So the main contributions in terms of hardware that we have is in this laser calibration system. So since the 80s, lasers were used to create tracks in gas detectors. It's harder to do that in liquid because you need higher intensities. Because we are ionizing, of course, it cannot be a single photon. It has to be a 3-photon process in liquids, but this can be achieved with very intense lasers. There was extensive R&D at CERN and then Bern University. So the concept of a laser for calibrating a large detector was then pioneered by Microboon. So the basic concept is that you have a very intense laser that the beam is steerable, cold mirrors in inverted periscopes throw the beam in the different directions, and then you compare the true and the reconstructed tracks. So if you have, for instance, electric field distortions in your detector, that will not affect the straight line that you know that your laser is going through. So any distortions that you see in the reconstruction need to be due to distortions on the electric field, and that's what you want to measure. Next slide, please. So uh, we proposed jointly with Los Alamos, we proposed to do this system for Dune, but of course, then one of um, the main issues, the main strategies for Dune is that everything needs to be tested at ProtoDune. So the ProtoDune effort is central to Dune. It's based at the neutrino platform that is a recently new, so 10 years old, a large experimental area in the Prevson site. So it uses beam charged particles from the SPS, and it has new infrastructure for large cryogenic detectors. You see that here. So there was an initial phase of the protodunes in which that ran until 2019, in which initial development of the technologies was tested, and then there was a second run of the protodunes that we are going through, in which the production modules have been tested. Next slide. So for this second run, we have built these ionization laser systems, and they were built entirely by us in the Los Alamos team. In the horizontal drift detector, this has run already last year. This is a picture of the detector with the system. So we basically have two lasers on the top that send beams down into the detector, either through openings on the top of the field cage or through the sides, through gaps on the field cage. We are testing several different designs, different periscope geometries. Some of them are proposed by us at LIP. Integration with the DAQ, that's also our responsibility, with the goal of testing this technology and also to providing calibrations for the detector. Next slide. So now I have here a few slides of pictures of the system. So we have the laser box and the electronics. So this was totally made by our colleague that is currently at LIP Minho at Braga. The beam is then sent down into the detector via these sets of mirrors. You see here on the right-hand side the feed-throughs that allow the beam to enter the cryostat and to move the mirror, the periscopes, and on the extreme right, the periscopes themselves inside the cryostat. Next slide. A few more details of our contributions. These are, a lot of contributions are mechanics, optics, and electronics. So we use extensively the infrastructures of LIP. There's excellent capabilities of engineering and mechanical workshop at LIP Coimbra. And there's also, as Nuno already mentioned, for Atlas, a lot of expertise on electronics as well. Next slide. Okay, so more pictures of installation at CERN. So we've set up a semi-clean room for tests and alignment of the periscope. So this is the team of Los Alamos and LIP. I think here I think I take advantage of this to mention that one of the real issues that sort of leads to having some success in this this new participation is the fact of choosing uh, a subject and a hardware participation in which you have some expertise and in which your lab can be there for you, and this is for sure the case with with mechanics and electronics, but also to have a good partnership, and that's what we have established already with the Los Alamos group. Next slide.
José, may I ask you to
So,
finish in 2 minutes?
oh, for sure. Yes, thank you. Yeah, so here's some images of the data that has been taken. So this is ongoing. We are now going to calibrate the second detector, and we are analyzing the data. Next slide. Yeah. Okay, so um, the um, the future will be calibration of the Dune FAR detectors. So because the proto-Dune laser systems so far have worked well, uh, we now have a plan to build this for Dune FAR detector. Basically, this is going to be done as a partnership as well, between LIP and Los Alamos. We will provide a lot of the machining and the electronics, and the LIP mechanical workshop will be heavily involved. Next slide. Okay, so construction status is that the caverns have finished. The cryostat parts have been already shipped, so that they have been built, and the installation inside of the cryostat starts in the next couple of months. The detector then inside the cryostats is 2027, 28, and so we'll be there for the calibration installations. And we expect physics with being physics 2029 and with being 2031. Next. The maybe I will go to the next one in the interest of time. So because we have these unique features of wide beam and long baseline, uh, Dune will be starting later than competing experiments. But in terms of mass ordering, the best sensitivity will be Dune and will catch up very quickly to the other experiments. Also, in terms of the sensitivity to the delta CP phase, it will have the ultimate sensitivity. Next slides. Yeah, so I wanted to mention this. There is already an ongoing collaboration with Brazil. So the Brazilian groups are responsible for, the development of the technology for the photon detectors of Dune. That this was invented at Campinas and is a major contribution to the FAR detectors of Dune. So this is tuned for the liquid argon scintillation, but they have developed other things. So next slide. The so-called Arapuca is developed for water Cherenkov effect, so it's actually a simpler design. So then, when I visited the Campinas University, and the thought there and the discussions was that could this be used for hybrid Cherenkov and scintillation detectors? So next slide. So hybrid Cherenkov and scintillation detectors is a proposed detector neutrino detector design that combines the high light yield of scintillation with directionality of Cherenkov light. So this could be a very big breakthrough for neutrino detectors. There's ongoing R&D, mostly in the US and Germany. A focus point here is the proposal of the TEA 25 kiloton detector that is proposed for the Dune FAR detector 4. So the first three detectors of Dune are going to be liquid argon, but there's the possibility to have a fourth detector that is not liquid argon. So our idea is to modify this Arapuca detection to separate Cherenkov and scintillation light, and we already have concrete plans to collaborate with the Campinas group starting next year. Okay, that's it. Thank you for your attention.
Thanks a lot for this very comprehensive talk. We have time for one question or comment. Maybe a quick question, José. So at the CERN site, so the program is to test always with beam. So that's protons. So like, what's the nature?
Protons, pions, electrons. I mean, one of the event displays I showed was positrons. But yeah, there's a variety of beams. So it's not a neutrino beam, although there is talk of doing that. I mean, there's already some active um, studies on identifying neutrino interactions in the protodune data set. You know, if the beam interacts further upstream in when it's providing um, beam for other experiments, then of course those interactions will produce neutrinos. They will still go downstream and hit the protodune detectors, and there's also a program there. But the main issue is to use protons, pions, and electrons.
Thanks a lot.
And yeah, and this will still be done for, I mean, this for the second phase of Dune. So it's not over the Proto Dune program for sure, because there is ongoing R&D for the third and the fourth detector, and so there's proposals already for the continuing the Proto Dune program for the next 5-6 years at least.
Thanks a lot. So let's think again, José. And now